Hi everyone and welcome to this ANSYS Workbench tutorial. In this tutorial we're going to be basing it off a case study from this book, Practical Stress Analysis with Finite Elements by Brian J. MacDonald. And we're going to be looking in particular at meshing 2D plane stress elements and how we'll do this in Workbench, how we can control the mesh and control the type of element that's used. So if we look in the book at case study C on page 363, we're presented with something like this. We're presented essentially with a beam problem. So we have a beam that's cantilevered into a wall at one end. It's 5 meters in length. It's got a height of 0.5 meters and a thickness of 0.05 meters. And it undergoes a vertical downward load of 2 kilonewtons at its tip. So we can use simple beam theory and we can find out the deflection of the point A, for example, using just elementary beam theory, turns out to be 0.768 millimeters or 7.679 by 10 to the minus 4 meters. Similarly, we can find out the stress using the beam bending equation. And so let's say we say the stress at the point B would be 4.8 by 10 to the power 6 pascals or 4.8 megapascals, and those calculations are given there. And again, there's more. This is done in detail in the book, so there's an entire chapter on this study that we're going to do here on the book. So we're going to assume that the material that the beam is made of is steel, and it's got a Young's modulus or elastic modulus of 210 gigapascals. That's 210 by 10 to the power 9 pascals. Poisson's ratio is 0.27. So on the next slide then we'll see what we do. Well, what we do is we make 5 different models. First we make a model which is just a beam element. So we're not going to cover that in this tutorial. That's up in one of the previous tutorials. So if you go back through the YouTube channel, you'll see one of the previous tutorials. We use beam elements and we make a bike model, or a model of a bicycle using beam elements. If you follow that, you can very simply make cantilever beam. You shouldn't have any problem there. What we're interested here in this tutorial is these 4 here. So the first model uses a constant strain triangle, in other words a 3-node linear triangle. So each of these triangles has 3 nodes and there's a linear shape function used in there, and we've basically got a line joining each of those nodes. Okay, and there's no mid-side nodes. The second one, model B, uses model C uses a 4-node linear quadrilateral element. So in this case, again, we've got 4 nodes. It's a rectangular quadrilateral shape, and again, we've got lines joining those 4 nodes. The next model, model D, uses a 6-node quadratic triangle. So in this case, each triangle has 6 nodes, and again, there's a quadratic shape function used there, so we can have curved lines joining the various points of the triangle. And the last one then is a Q8 element, or an 8-node quadratic quadrilateral. Okay, so it's this one here. So we've got 8 nodes and we can have curved edges. Okay, so we have quadratic interpolation. So we're going to look at how to build each of these models. So in particular, this can be challenging in Workbench because Workbench tends to try and help you, which is a good thing, to make a better model, and some of these models aren't good. So we'll see this one in particular is not a good idea. So if going through the case study in the book, then next thing you'll be presented with is the summary of results from the initial model of each type. So the initial model is literally the one shown here. So in the case of the constant strain triangle, we've got 4 divisions along the length and 2 divisions along the thickness. And again, the same with the Q4. And again, in fact, all of them are the same. So they've all have 4 divisions along the length and 2 divisions across the across the height. So we're going to look at these initial models. So you can see that for when we had one beam, we got a deflection of 0.762 and a stress of 4.8 megapascals. Again, if you go back to the theory, you'll see that that's pretty much spot on the theory. And again, you see there that gives us a 99% and 100% accuracy for deflection and stress. However, when we look at the constant strain triangle, which has 16 elements, we get a deflection of 0.089 and a stress of 0.5. So that's 11% and 10% accurate. So that's very, very bad. So this one here, those 3-node triangles do not give very good results. And there's reasons for that, which are explained in more detail in the book. If we look at this one here, the Q4, 8 of those gives us 96%, 87% accuracy. The linear strain triangle, which is this one here, the quadratic triangle, gives only 16 of those, gives us 98% and 93% accuracy. So it's interesting to compare that to the 3-node triangle, same amount of elements, and we go from 11 to 98 and 10 to 93% accuracy. And then for the Q8, 8 of those gives us 98% accuracy as well. So let's jump over to Workbench, and the first thing we're going to do is we're going to try and build this one here, the constant strain triangle, and we're going to use the information shown on this slide here to help us build that. So I've opened up Workbench, and the first thing I'm going to do is click on static structural and drag that over here to create a static structural instance in Workbench. Then I'm going to go into my engineering data, and I'm going to double click there. There already is a structural steel in Workbench, which is kind of similar to what we want, but not exactly the same. So what I'm going to do here is I'm going to click New Material and call it My Steel. Again, you can call that whatever you want. Then I'm going to go over here to isotropic elasticity and double click on that. And it's going to give me a new a table for isotropic elasticity. And I'm going to put in the values from the case study. So 210 e to the 9 pascals, and Poisson's ratio was 0.27. Okay, so now that that's done, my material is set up, and it's set up as my steel. So I can close my engineering data. I'm going to click on geometry. The first thing I'm going to do is come over here and change the geometry from 3D to 2D, because I'm going to do a plane stress analysis. You can use Space Claim if you want to make the geometry. I'm going to use Design Modeler, so I'm going to right click on geometry and I'm going to say New Design Modeler Geometry, and then I'm just going to wait for that to open up. Okay, so now I'm in Design Modeler, and what I want to do is I want to create my model of the beam. So I'm going to draw on the select the XY plane. I'm going to say look at plane, and I'll just briefly go over to the outline again, showing the geometry. So you can see I want a beam that's 5 meters long, 0.5 meters high, and 0.05 in thickness. So 5 meters long and 0.05 are the ones I need immediately. So back in Workbench then, I'm going to click on Sketching, and I want a rectangle, and I'm just going to draw a rectangle here, something like that. And then I can just zoom in a bit on this. Let's just zoom extents there, zoom out a little bit. And now I can put some dimensions on that. So I'm going to dimension the horizontal first of all. And I want that to be 5 meters. So I'll just put 5 in here. And then I'm going to dimension the vertical. And again, I want that to be 0.5. Okay, so now I have my 5 meter long beam, 0.5 meters high. Okay, so I can go back into modeling now, and if I expand the XY plane, I'll see my sketches there. I'm going to go to Concept, Surface from Sketches. It's asking me which base object do I want, so I'm going to click on Sketch 1 and then click on Apply. Then it's also going to say, well, what thickness do you want? So if you remember, the thickness was 0.05. I'm just going to put that in. And now I can just click on that and click Generate. So now I have my surface body. There it is, right there. So I'm all done with the Design Modeler now. I can shut that down. And now when I go back to my Workbench, you'll see that there's a tick on my geometry. And now what I want to do is open up the model to build the finite element model. So I'll double click on that and wait for that to open. Okay, so here I am in the modeler, in my finite element model. First thing I'm just going to do is look at geometry, and it tells me, well, I've got a surface body. At the moment it's got the structural steel assignment, so I'm just going to change that and change that to my steel. So now it'll be using the material properties that I put in. You'll see that then turn up there. And now I'm going to straight down to mesh. So first first of all, here we see in the defaults we've got mechanical, which is good. Then we have element order program controlled. The first thing I want to do there is change that to linear because I want the linear triangles. Then in mesh, I'm going to right click and I'm going to go insert face meshing. I'm going to click the face and I'm going to go apply. And then it's going to say, well, what do you want to do? I want a mapped mesh, yes. And I don't want quads, I want triangles. Okay. Then the next thing I want to do is I want to split this into 4 divisions and this one into 2 divisions. Okay, so right now if I was just go and mesh it, let's just go ahead and do that. Workbench is going to try and do what it thinks is a good mesh for me. So to be fair, it's trying its best here. It's split it up into maybe 20 divisions and 3 divisions across, which is the right thing to do with this type of element because it's not very accurate unless there's a lot of it. So I'm purposely trying to do it inaccurate here to demonstrate how this element is inaccurate. So, but having said that, it's a good way to learn how to really control meshing in Workbench. So now what I'm going to do is I'm going to go insert sizing, and I'm going to pick the make sure my selection filter up here is selected to edge. I'm going to pick the top edge. I'm going to hold down the control key and hit the bottom edge. I'm going to go OK. And here, instead of element size, I'm going to say I want number of divisions. And for number of divisions, I want 4. Very, very important that I change this one here from soft to hard. Okay. I'm going to not change it for the moment, just to demonstrate what happens. Okay. So, similarly then, I'm going to insert a new sizing on the same thing again, this end and this end. And go apply, and again I'm going to say number of divisions and number 2, and again I should change this to hard, but I'm not going to for the moment just to show you what happens if I don't. Okay, so let's just go ahead and tell it to mesh that. So even though I put in the 4 and the 2 and the 2, nothing's happened because I didn't select the hard. Okay, so let's just go back and change that. So again, just change that to hard, and again change this one to hard. And let's just try it again. So now I've gotten exactly what I've put in. Okay, and it's giving me a warning. So some element, let's just click on that. The warning that I got then is some local element face sizes are larger than the global maximum size. This can usually cause bad quality elements. So it's that warning is correct. These elements are not great, and I'm purposely having them like that. So it's very, very important that when I'm doing the sizing, I change it to hard, or else the algorithm, the good meshing algorithm in Workbench will override my bad choices. Okay, but I don't want it to in this case. So now let's just set up this solution. So I just go down to structural static, and I click on insert. And the first thing I want is a fixed support. So I want a fixed support on that end and just go OK. And the next thing I want is a force on the opposite end. Click that, go OK. I don't want a vector, I want it in components. And the Y component, it was 2 kilonewtons. So I'm going to do it in minus 2000. There's my load going down there. Now from the solution information, so if you look at the book, one of the things we're asked for is stress in the X direction and also displacement in the Y direction. Okay, so I'm going to insert stress, normal, and the orientation is X, so that's fine. And I'm going to insert deformation, directional. In this case, I want it in the Y axis. So now I'm all ready to solve, so always a good idea just to do a quick save. Okay, and now I can solve my problem, which should be very quick because it's a reasonably simple model. Okay, so there's my solutions. The first thing is my stress, my normal stress. So you can see that I'm getting a stress here of minus 2.7 and plus 5, and then my directional deformation is 8.8711 e to the minus 5. So you can see that's quite different to the that predicted by the beam theory. So if we very quickly were just to look at that again, so the beam theory tells me that my deflection should be 0.768 millimeters and my stress should be 4.8 megapascals. Okay, so again, my deflection is actually e to the minus 5 instead of being e to the minus 4, so it should be 7 e to the minus 4, and here I've got 8 e to the minus 5, and my stress again should be in megapascals. So if we just take a look there, my stress should be 4.8 megapascals, so you can see that my stress in this case is way off. Okay, so again, if we just take a look at the information in the book, when we get to the table of comparison of results here, I'm getting pretty much what's in the book. Okay, I'm getting a deflection of 0.089 millimeters and a stress of about 0.5 of a megapascal. Okay, where I should be getting stress about 4.8 megapascals and deflection by 0.7. So I'm an order of magnitude out. So I'm getting more or less exactly the same results that are in the book. Okay, so the most obvious way to change this model is to turn the linear elements into quadratic elements. Okay, so let's go and do that. Let's go back to mesh and let's just change element order to quadratic. Okay, so you can see everything has changed. Okay, I need to remesh and resolve. Okay, because I've just done that. So instead of just being one node at each corner, now there'll be mid-side nodes as well. Okay, so let's just generate that mesh. Okay, so now I have a quadratic mesh. Again, it's telling me still should probably remesh this a bit, but that's fine. Let's go ahead and solve it now and see what happens. So again, my solution shouldn't take that long. Okay, so now let's look at my normal stress. Now I'm getting 4.6 megapascals. So 4.6 e to the 6 pascals. Remember the last time I had 5 e to the 5. Okay, so I'm getting what I expect now. And in terms of directional deformation, I'm getting 0.007. So I'm getting like 0.7 of a millimeter. So again, just to kind of go back, that is what I'm looking for. So I'm looking for 4.8 and 0.7, and I have gotten 0.7 and 4.6. Okay, so I'm not exactly on it. So again, a little bit of remeshing would improve that. Okay, so the last thing then is let's go and change from triangles to quads. So we have face meshing back in here, and we have triangles. Let's change to quads, and also let's go back and tell it to go back to linear. Okay, so now we've got the linear quads, so let's try this one. Okay, so there we go, we've got 8 elements. Okay, again, let's solve it again. So I should get more or less the same kind of result this time. Okay, there again, my stress is 4.1, so rather than 4.6 the last time, so it's a little bit more inaccurate. And my deformation is quite accurate. So again, this is kind of mirroring what's in the book. If you look at the constant strain triangle was giving me 11%. The linear strain triangle was giving me 98%. The Q4, which is the one I'm looking at now, was giving me 96% and 87%. So 4.16 in the book. Stress here 4.16. So again, I'm getting more or less the same results that are in the book. And then the final one is to go back in and just change to the quadratic. So the 8 node element. So again, let's just go in here and change the linear to quadratic. And again, you can see everything changes because it needs to be remeshed. And generate mesh. And then just solve again. And now if I look at my normal stress, I've got bang on 4.8 megapascals. And my direction 7.6 roughly. So again, 0.76 is 5. Okay, a little bit off, 0.763. And stress again 4.87. and my stress that I'm going for is 4.8. So again, very, very accurate. Okay, so 8 of these elements is giving me a very, very accurate result, whereas the other ones, the amount of elements we have, weren't giving us as accurate as 8 of these. So these ones are proving to be the most accurate. So sometimes it may not be kind of clear that there is the number of nodes they are here. So a very easy way to check this is to go up here and go to the select node. Okay, so this one here. And what that will let me do is if I hold that down, you can see that as I move it around, it's selecting the nodes. Okay, so this one has 8 nodes. Okay, so again, you see we have the mid-side nodes in this case. So again, if I was to just go back now and go a little bit backwards and change the element order from linear, or sorry, from quadratic to linear, just remesh that again. Now if I try and do the same thing, select nodes, now you'll see that there's only nodes on the corners. Okay, it's not selecting, there's none on the inside. Okay, so it's just a quick way of actually just checking that you've got the nodes that you expect to have. So another good way of doing this is to go into the at the top here, to go into display and click on annotation preferences, and in there you can turn on node numbers as well. So if I go OK there, you can see that we have the node numbers turning up. Again, sometimes they could be hidden behind the structure, so you might actually want to go here and change the wireframe. Okay, so you can see I have my node numbers there. Again, let's just go and change that again. So let's go and change it to quadratic, just so we can see that the extra ones do appear. So now if I remesh that, okay, so now you can see I have my mid-side nodes turning up as well. Okay, so again, just annotation preferences and node numbers. Okay, so you can turn that on and off if you want. Okay, and again, just to go back to the wireframe mode, or you can just click this button here as well. So this tutorial was really just a way to show you how to get more control over your 2D meshes using ANSYS Workbench, how you can change between linear and quadratic elements, how you can force a model to be meshed according to the divisions that you set, and just again changing that hard and soft option, and how important that is, and also how you can check the number of nodes that you have in each element and that you are in fact getting a linear or a quadratic element. So again, I would encourage you to get a copy of the book and take a look through this case study in the book, and again, try this out, make sure that you're getting the same results that are in the book, as we went through it there, and we got pretty much exactly the same results, maybe just off a little bit. Again, the book can be found on Amazon and all good book retailers. Okay, so that's it for this one. Thanks, bye.